The cosmos is not silent. We are surrounded by a constant hum of cosmic noise, a background radio whisper from stars, gas, and the afterglow of creation itself. But sometimes our telescopes pick up a sound that does not belong. A sharp crackle, a repeating pattern, a signal so strange it defies every easy explanation. These are the universe's encrypted messages, and we are only beginning to learn how to listen. Today, we embark on a journey through 25 of the most enigmatic signals ever detected, from bursts of energy that outshine galaxies to whispers that once made scientists wonder if we were not alone. By the end, you will understand the profound mysteries these cosmic puzzles represent and how each one, solved or not, redefines our place in the stars. We will confront a signal so powerful it was circled with the word wow and investigate repeating patterns from the deepest voids. What you believe is waiting for us in the cosmic static. It began with a single sheet of paper. On the night of August 15, 1977, a radio telescope at Ohio State University known as Big Ear was performing a routine sky survey, listening to the endless static of space. The data printed out line by line on continuous feed paper, a string of letters and numbers representing the signal strength from each tiny patch of sky. For the most part, it was a monotonous job, a sea of ones and zeros. But one line from a region of space near the constellation Sagittarius was different. It showed a sequence so powerful and so strange that the astronomer reviewing the data, Jerry Amon, felt compelled to grab a red pen. He circled the entire sequence and wrote one word in the margin, a word that would echo through history: wow. The signal itself was a string of 6 characters, 6EQUJ5. To the untrained eye, it looks like gibberish, but to a radio astronomer, it was a scream in the silence. Each character represented a signal intensity far above the background noise. The sequence spiked up to 30 times the normal cosmic chatter and lasted for a full 72 seconds, the exact time it took for the Big Ear telescope's field of view to pass over that fixed point in the heavens. And then, just as suddenly as it arrived, it vanished. Decades of follow-up observations, using far more sensitive equipment, have listened to that same spot over and over again. They have heard nothing, not a whisper, not an echo. The wow signal was a one-time event, a cosmic door that slammed shut the moment we glimpsed inside. Its origin point is tantalizing. It came from a direction with no known stars or planets at the time, a seemingly empty patch of space. This void of a source fueled endless speculation. Could it have been a natural event we simply do not understand, like a comet's outburst or a strange form of stellar flare that we have never seen before? Or was it something else entirely, the first and only time we have ever intercepted a transmission not meant for us? The signal occurred on a frequency close to the hydrogen line, a universal marker that many scientists believe would be a logical channel for any civilization attempting to announce its presence. The coincidence is haunting. What makes the wow signal the gold standard of cosmic mysteries is its perfect, frustrating purity. It was strong, it was clear, it was seemingly artificial in its narrow frequency focus, and it is utterly unrepeatable. In science, repeatability is everything. A phenomenon that cannot be observed again becomes a ghost, a story told by a single instrument on a single summer night. It resists all explanation by refusing to show itself a second time. So the wow signal endures not as an answer, but as the ultimate question. It is a reminder that the universe is capable of producing moments of shocking specificity that we, for all our intelligence, may never fully comprehend. It is the siren song of the cosmos, a call from the dark that we heard once and have been straining to hear again ever since. The wow signal was a single shout in the dark, then fast radio bursts are the universe's staccato screams. These are not gentle whispers but titanic explosions of energy, compressed into blasts that last mere thousandths of a second. In that fleeting moment, a single fast radio burst can release more energy than our sun will emit over 80 years. The discovery came in 2007, not from a live observation, but from a stroke of archival luck. An astronomer named Duncan Lorimer was sifting through old data from the Parkes radio telescope in Australia, recorded 6 years prior when he found it, a spike of radio waves so intense and so brief it had been initially dismissed as terrestrial interference, a glitch from a passing satellite or a microwave oven. But this was no kitchen appliance. The signal had traveled across billions of light years, and it carried the distinct fingerprint of a journey through the diffuse gas between galaxies. It was a message from the distant cosmos written in interstellar static. The sheer power of these bursts immediately presented a profound mystery. What natural engine in the universe could possibly be so efficient, so brutally powerful, as to focus such staggering energy into a blink of an eye? For years, every fast radio burst detected was a one-off event, a cosmic flashbulb popping once and never again. This made them nearly impossible to trace, their origins lost in the vastness. But then, in 2016, everything changed. Astronomers confirmed that a burst designated FRB 121102 was repeating. It was not a single catastrophic explosion, but a source that could fire again and again. This was the break scientists desperately needed. Because it repeated, they could point the world's most powerful telescopes at its location and hold their gaze. They traced the repeating bursts back not to a giant galaxy, but to a small, turbulent dwarf galaxy over 3 billion light-years away. Inside that unassuming galaxy, the source was pinpointed to an incredibly powerful and bizarre environment, a region near a supermassive black hole or a potent nebula of magnetized gas. The repeater proved these were not just random final death throes of unknown objects, but phenomena that could persist, that had a home. It meant the universe had at least two ways to produce these brilliant flashes, one that destroys its source and one that does not. The existence of repeaters transformed fast radio bursts from cosmic ghosts into tangible, if utterly bewildering, inhabitants of the distant universe. The discovery of repeating bursts meant scientists finally had a target, a cosmic laboratory where they could test their wildest ideas. So what cosmic engine could possibly produce such violent, fleeting flashes? The leading suspect is a magnetar, a type of neutron star with a magnetic field so powerful it could strip the information from a credit card from halfway across the solar system. Picture a dying star's core, crushed into a city-sized sphere spinning faster than a kitchen blender and wrapped in magnetic fields trillions of times stronger than Earth. This creates an environment of unimaginable stress. Astronomers theorize that these stars can experience starquakes, sudden ruptures in their rigid crust, or episodes where their twisted magnetic fields snap and reconnect. Either event could unleash a cataclysmic blast of energy that ripples across the universe as a fast radio burst. In April 2020, a magnetar within our own Milky Way galaxy, named SGR 1935+215, did something extraordinary. It erupted not just with X-rays, which these objects are known for, but with a simultaneous radio burst that looked, for all intents and purposes, like a weaker cousin of the distant cosmic fast radio burst. This was a monumental clue, a smoking gun in our own galactic backyard. It proved that at least some of these mysterious signals could indeed be born from the apocalyptic tantrums of these magnetized stellar corpses. But does that solve the entire puzzle? Not even close. The fast radio burst from our galactic magnetar was thousands of times weaker than the colossal blasts coming from billions of light-years away. This suggests that while magnetars might be one source, the most extreme bursts could require something even more violent, or perhaps a magnetar in a uniquely destructive environment, like one being swallowed by a black hole or colliding with another dense object. This leads to other compelling theories. Could some fast radio bursts be the final death cry of two neutron stars spiraling together and merging, an event so energetic it warps the fabric of spacetime itself? Or might they be produced by phenomena so exotic they border on science fiction, like cosmic strings, theoretical defects in the structure of the universe left over from the Big Bang? And of course, the sheer precision and power of these bursts inevitably raises a more speculative question. Could a sufficiently advanced civilization generate such signals, perhaps to power interstellar light sails or as a byproduct of technology we cannot fathom? While the galactic magnetar discovery strongly favors natural, if extreme, astrophysics, it has not entirely closed the door on wonder. The truth is, fast radio bursts are likely not one mystery but many. They may be a cosmic language with multiple dialects, each representing a different catastrophic event in the life story of stars. Every new burst we detect, especially the repeaters, is another piece of a puzzle that is forcing us to rewrite the book on how the universe can scream. Buried in the data, hidden for years, was the very first cosmic scream we ever recorded. This signal, now known as the Lorimer burst, or FRB 010724, was the original fast radio burst, the one that started it all. Its story is one of pure serendipity. In 2007, astronomer Duncan Lorimer and his student were not looking for anything new. They were meticulously reviewing old data from the Parkes Radio Telescope in Australia, searching for distant pulsars. The data was from July 24, 2001, nearly 6 years old. As they scanned the printouts, one entry stood out like a lightning bolt on a clear night. It was a single, monumental spike of radio energy, a pulse lasting just 5 milliseconds. In that sliver of a second, it released more energy than our sun emits in a month. The signal had a peculiar trait called dispersion, where lower frequency radio waves arrive slightly later than higher ones, a telltale sign of a long journey through the thin plasma between galaxies. This meant it was not local, not from Earth, not from our solar system. It was profoundly, undeniably extragalactic, yet for all its power, the discovery was met with deep skepticism. The scientific community's first reaction was not excitement but doubt. A signal so bright and so brief had to be an error, a terrestrial glitch. Could it have been a satellite passing through the telescope's beam? Or perhaps interference from some earthly electronic device? The fact it was found only in archived data, a one-time event that could not be recreated, made it even harder to accept. For a time, the Lorimer burst was treated as a fascinating anomaly, a cosmic ghost story that most astronomers were hesitant to believe, but its existence, once proposed, could not be ignored. It was a challenge written in radio waves. That single, unrepeatable pulse forced scientists to ask a dangerous and thrilling question: what if it was real? What if the universe was filled with these explosive whispers and we had only just begun to hear them? The Lorimer burst, this lonely signal from the archives, became the foundation. It proved such phenomena could exist, providing the template for what to look for. It turned a dismissed glitch into a blueprint, paving the way for dedicated searches that would soon uncover dozens, then hundreds of these bursts. Without that first, skeptical glance at old data, the entire thrilling field of fast radio burst research might not exist today. It stands as a monument to the power of paying attention, a reminder that sometimes the universe's greatest shouts are found not by looking forward but by listening to the past. There is another kind of signal, one that was not found by a giant telescope but by millions of ordinary computers. In 2003, the SETI at Home project, which uses the spare processing power of volunteers' personal computers to analyze radio telescope data, flagged something strange. It was a weak, persistent whisper designated SHB 02+14A. On the surface, it had three tantalizing features. First, it pulsed at a frequency near 1420 MHz. the emission frequency of neutral hydrogen, the most common element in the universe and a logical channel for interstellar communication. Second, it appeared to originate from a point in the sky near the constellation Pisces, a region with no obvious stars. Third, and most provocatively, the signal exhibited a very slight frequency drift. This drift could be interpreted as the Doppler shift caused by a transmitter on a rotating planet, its motion slightly compressing and stretching the signal as it spun. The implied rotation rate was startlingly close to that of Earth. For a moment, it seemed like the dream of SETI at home had come true, a potential artificial signal sifted from the cosmic noise by a global network of home computers. The excitement, however, was met with immediate and profound skepticism from the broader scientific community. The signal was extremely faint, hovering right at the threshold of detectability. Critics argued it was far more likely to be the product of random noise combining in a statistically unlikely way, or interference from a terrestrial source that the distributed software had mistakenly pieced together. The biggest strike against it was its behavior. A genuine signal from a distant world would be expected to originate from a fixed point in the sky as Earth rotates, but as it should be 02 plus 14, seemed to wander, not holding a steady position. This pointed strongly to an origin much closer to home, perhaps a glitching satellite or an unnoticed piece of electronics. Despite numerous attempts, the signal was never heard again, sealing its fate as an unconfirmed candidate. It remains a ghost in the distributed machine, a testament to both the power of citizen science and the immense difficulty of the search. It embodies a core truth of the hunt for extraterrestrial intelligence, the heartbreaking work of separating the faintest whisper of a hello from the universe's endless, indifferent static. The hope for a whisper from next door arrived in December 2020. Astronomers with the Breakthrough Listen project, a monumental effort to scan 1 million stars for signs of intelligence, detected something extraordinary. A narrowband signal, precisely at 982 MHz, seemed to be emanating from Proxima Centauri, the closest star to our Sun and home to at least one known rocky planet. This was not a cosmic blast, but a quiet, persistent hum on a specific frequency, the kind of signature a technological civilization might produce. The signal, named BLC-1, did not drift. It held its frequency steady as the star moved across the sky, suggesting it was not from a satellite or a plane. For a moment, the dream felt startlingly real. A potential technosignature was not from a distant galaxy, but from our very own cosmic backyard, a mere 4.2 light-years away. The initial analysis was electrifying. Here was a candidate that passed every initial filter, a signal that behaved exactly as theorists predicted an artificial one would. The implications were staggering. Had we just heard our nearest interstellar neighbor, the excitement, however, was tempered by a rigorous and deliberate process. Breakthrough Listen did not announce a discovery, they announced an anomaly worthy of intense scrutiny. Over the following months, a global team conducted a forensic investigation. They pointed other telescopes at Proxima Centauri, searching for a repeat of the signal. They analyzed the signal's characteristics with microscopic detail. The truth, when it finally emerged, was a lesson in humility. The signal was almost certainly human-made interference, a false positive. The most likely culprit was a poorly calibrated electronic device on Earth's surface, or perhaps a satellite that had not been properly accounted for in the complex models of radio frequency interference. Its apparent stability relative to the star was a cruel coincidence of timing and geometry. BLC-1 was not a hello, but an echo of our own technological noise bouncing back at us. Yet this story is not one of failure, but of profound progress. The meticulous, transparent process of investigating BLC-1 has become a blueprint for the future. It demonstrated how modern SETI works, not as a rush to judgment, but as a careful, skeptical elimination of all terrestrial possibilities. It proved our detection systems are sensitive enough to find needle in a haystack signals, and more importantly, it strengthened the protocols for verifying the next candidate. BLC-1 is a milestone because it showed us what a real detection might look like, and it hardened our resolve to tell the difference between our own reflection and a true face in the cosmic dark. The search for intelligence often leads to discoveries of a different kind, revealing not civilizations but cosmic clockwork of breathtaking precision. In 1967, a young graduate student named Jocelyn Bell Burnell was reviewing data from a new radio telescope she had helped build in Cambridge. She noticed a peculiar bit of scruff on the chart recorder, a faint, rhythmic pulse that appeared and disappeared with the rotation of the Earth. It was not a constant signal, but it returned to the same spot in the sky every 1.337 seconds with a regularity more perfect than any known natural object. The pulse was so steady, so unnervingly artificial in its timing, that the small research team half-jokingly labeled the source LGM-1 for Little Green Men 1. Could this be a beacon, a cosmic lighthouse built by an advanced society to mark their territory or communicate across the void? The possibility, however remote, had to be seriously considered. For a few thrilling and anxious weeks, they explored the idea of a technological origin, even devising tests to see if the signal carried any encoded information. The truth, when it came, was far stranger than anyone had anticipated. Further observations revealed not one, but several of these pulsing sources across the sky. They were not the product of intelligence, but of physics pushed to an extreme. The team had discovered the first pulsar, a rapidly spinning neutron star. This is the collapsed core of a massive star that has exploded, a sun's worth of mass crushed into a sphere just a dozen miles across, spinning faster than a kitchen blender and beaming out intense radiation from its magnetic poles like a cosmic lighthouse. As it spins, this beam sweeps past Earth, creating the perfectly timed pulse we detect. The LGM-1 signal, which sparked dreams of contact, was actually the death spin of a stellar corpse. This transformation is one of science's most beautiful stories. A mystery born from the hunt for aliens did not vanish with an answer. It blossomed into an entirely new field of astrophysics. Pulsars became universal tools, natural laboratories for testing gravity, mapping the galaxy, and even serving as potential navigation beacons for future interstellar travel. The story of LGM-1 teaches us that the universe's greatest enigmas are not dead ends but doorways. Sometimes the signal we mistake for a hello is the universe introducing us to a fundamental truth we never knew to look for. The dream of a signal from a nearby sun flared again in 2015, this time from a star with a known planet. Russian astronomers using the colossal Rattan 600 radio telescope reported detecting a strong, narrowband signal from the direction of HD 164595, a sun-like star about 94 light-years away in the constellation Hercules. This star was already known to host at least one Neptune-sized world. The signal, quickly nicknamed the Periton signal, was a powerful spike at a frequency of 11 GHz, and it had a curious property. It was heard only once as the telescope's beam swept across that point in the sky, a signature that could suggest a non-repeating, deliberate transmission. When the news quietly reached a small group of scientists a year later, it ignited a brief but intense media firestorm. Headlines asked if we had finally found evidence of an advanced civilization. The speculation was fueled by a tantalizing calculation. If the signal was an intentional broadcast meant to announce a civilization's presence to the galaxy, it would require a staggering amount of power, equivalent to harnessing the entire energy output of a star. But if it was a more focused beacon, deliberately aimed at our solar system, the power requirement dropped to something still immense, but conceivably within the realm of a Type 2 civilization on the Kardashev scale, a society that masters the energy of its own star. For a few days, the possibility hung in the air, electrifying the public imagination. The scientific response, however, was swift and systematic. The SETI Institute immediately trained the Allen Telescope Array on HD 164595, listening across a wide range of frequencies. The Breakthrough Listen project used the Green Bank telescope to conduct its own exhaustive search. For over 2 months, the world's most sensitive ears listened intently to that star. They heard nothing, no repeat of the signal, no anomalous whispers, only the ordinary silence of space. Without that crucial repeatability, the signal's credibility evaporated. The overwhelming consensus became that the Periton signal was almost certainly not a cosmic hello. The most likely explanation was terrestrial interference, perhaps from a secret military satellite or other human-made source that briefly drifted through the telescope's field of view. It could also have been an instrumental artifact, a glitch within the complex electronics of the telescope itself. The story of the Periton signal is a masterclass in the modern scientific process, a rapid cycle of detection, excitement, rigorous verification, and sober conclusion. It underscores a fundamental and frustrating truth in the search for extraterrestrial intelligence. A single, unrepeatable signal, no matter how promising, is simply not enough. The universe is noisy with our own technology, and our instruments are imperfect. To prove we are not alone, we do not need just a whisper, we need a conversation, a signal that says hello, and then says it again and again, proving it is real. But sometimes the universe does not speak in radio waves, it winks at us in starlight. Far beyond our solar system, a star designated KC 8462852, better known as Tabby's star, began to behave in a way that defied every textbook. The Kepler Space Telescope, designed to hunt for planets by watching for the tiny, regular dips in starlight caused by an orbiting world, found something utterly different here. Tabby's star did not dip by a neat fraction of a percent at predictable intervals. Instead, it plunged into darkness erratically, sometimes dimming by a staggering 22%, as if something colossal and misshapen was drifting across its face. These were not the clean transits of a round planet. They were deep, jagged, and chaotic, a pattern unlike anything seen around any other star in the galaxy. The strangeness did not end there. Long-term data revealed the star was also undergoing a mysterious, long-term fading, growing dimmer over years. This combination of sudden, deep eclipses and a slow, secular dimming sent astronomers scrambling. What natural object could possibly block that much light in such an irregular way? The initial mundane explanations fell short. A swarm of comets was proposed, a vast family of icy bodies breaking up and casting immense shadows. But the scale required was almost unimaginable, hundreds of thousands of giant comets in a precise orbit, a scenario that strained the laws of orbital dynamics. A recent collision between planets could create a cloud of debris, but such an event would be incredibly rare and short-lived while the dimming of Tabby's star persisted. When every conventional answer seemed inadequate, an extraordinary idea floated into the discussion, one born of science fiction but treated with scientific seriousness. Could we be witnessing a partially built alien megastructure? The concept, known as a Dyson swarm, involves a civilization capturing the energy of its star by surrounding it with a vast array of solar-collecting satellites or habitats. Such a structure would be irregular, blocking light in strange, non-repeating patterns, and could explain both the deep dips and the long-term dimming as more collectors were added. For a time, Tabby's star became the most compelling candidate for evidence of advanced civilization, not from a radio signal but from the shadow of their engineering. The scientific community responded not with dismissal but with intense observation. Ground-based telescopes and space observatories were trained on the star, analyzing the light across every wavelength. The key clue lay in the color of the dimming. When a solid object like a planet or a megastructure passes in front of a star, it blocks all colors of light equally. But when the dimming is caused by diffused dust, the shorter wavelength blue light is scattered more than the longer wavelength red light. The observations were clear. The dimming was more pronounced in blue light than in red. This was the fingerprint of dust, not solid metal or rock. The most likely culprit now appears to be a vast, uneven cloud of fine dust particles, perhaps from the disintegration of a moon or a family of asteroids orbiting the star in a clumpy, chaotic ring. While this natural explanation fits the data, it does not erase the profound impact of the mystery. Tabby's star forced astronomers to think in radically new ways. It demonstrated that when nature presents a puzzle that resists all standard solutions, even the most speculative ideas must be considered and rigorously tested. The star remains an enigma, a reminder that our galaxy is capable of producing phenomena we have never seen before, and that sometimes the shadow of a dream can lead us to a deeper understanding of cosmic reality. The shadow of a distant star fades, but a whisper from a neighbor can be just as perplexing. In 2017, astronomers at the Arecibo Observatory in Puerto Rico were conducting a routine survey of nearby red dwarf stars, small and faint suns that are the most common in our galaxy. Their focus was on Ross 128, a quiet star just 11 light-years away, a stone's throw in cosmic terms. As they pointed the giant dish toward this stellar neighbor, they detected something utterly unexpected, a series of strange broadband signals. These were not the narrow, artificial-sounding beeps of a potential broadcast, but rather wide, dispersive bursts that seemed to have a quasi-periodic structure, repeating in a pattern that was almost but not quite regular. For about 10 minutes, the star seemed to come alive with a bizarre radio chatter unlike anything seen from a red dwarf before. The proximity of the source made the mystery all the more urgent. At such a short distance, the possibility of a planetary origin, however remote, could not be immediately dismissed. Could this be the radio signature of intense stellar flares interacting with a planet's magnetic field, or something even more unusual? The scientific team, led by Professor Abel Mendes, did something crucial. They publicly announced the anomaly and invited the global community to help solve it. They outlined the three leading hypotheses: interstellar scintillation from the star itself, an outburst from a high-orbiting satellite, or a flare from some other object in the same field of view. A coordinated campaign of follow-up observations was launched using both Arecibo and the Green Bank telescope. The key was to look again under different conditions. When they pointed Green Bank at Ross 128, the strange signals were gone. But when they pointed it at other celestial objects, they sometimes detected similar bursts. This was the telltale clue. The signals were not tied to the star, they were tied to the line of sight from our rotating planet. The final verdict pointed not to the cosmos, but to our own orbit. The most likely culprits were one or more geostationary satellites, those human-made objects that hang in a fixed position over Earth. As Arecibo's beam swept across the sky, it would occasionally intersect the distant radio emissions from these satellites, which, due to their high altitude and relative motion, created the illusion of a quasi-periodic signal from a fixed star. The Ross 128 flare was a masterclass in cosmic humility. It demonstrated that even the most experienced observers, using the world's most powerful instruments, can be fooled by the ever-growing shell of our own technology. It underscored that before we can hear the universe, we must first learn to recognize the sound of our own voice echoing back from the machinery we have sent into the sky. The Ross 128 incident taught us to filter out our own noise, but to truly understand the universe's screams, we needed to stop listening to one star at a time and start hearing the entire sky at once. That revolution arrived with a strange-looking instrument in the mountains of British Columbia, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Unlike the giant, steerable dishes of traditional radio telescopes, CHIME is a fixed array of 4 massive half-pipe cylinders resembling a sprawling skate park for giants. Its design is its genius. It has no moving parts. Instead, it uses digital wizardry to stare at a gigantic strip of sky overhead every single day, processing an ocean of radio data in real time. This made it the perfect net to catch the ephemeral flashes of fast radio bursts. Since it began full operations, CHIME has transformed the field from a hunt for rare ghosts into a study of a cosmic population. It has detected hundreds of new fast radio bursts, more than all other telescopes combined, and critically, it has found dozens of new repeaters. This flood of data is like moving from studying a few mysterious footprints on a beach to having a live video feed of the entire coastline. We are no longer asking what a fast radio burst is. We are starting to ask what kinds of fast radio bursts exist. The census from CHIME is revealing categories. There are the one-offs, the titanic explosions that likely destroy their source. And then there are the repeaters, which seem to be a distinct class, often less energetic but capable of firing over and over again from the same spot. By mapping the locations of hundreds of these bursts, CHIME has shown they are spread evenly across the sky, proving they originate far beyond our Milky Way, in galaxies across the universe. This distribution is a crucial clue. It means the engine that produces them is not some rare local fluke, but a common, perhaps even universal, part of cosmic evolution. Among the many repeaters CHIME has found, a few stand out as cosmic laboratories. There is FRB 180916, which repeats with a predictable 16-day cycle, active for 4 days and silent for 12. This remarkable periodicity points to an origin in a complex binary system, perhaps a neutron star orbiting another star or black hole, where the companion's gravity periodically modulates the burst. Another, FRB 20190520b, is notable for being one of the closest and most active repeaters known, giving us a clearer signal to dissect. By studying the subtle twists in the polarization of light from these repeating bursts, astronomers have been able to probe the magnetic environments around their sources, confirming they are often in incredibly turbulent, magnetized places like the regions near supermassive black holes or within dense star-forming nebulae. CHIME ongoing census is doing more than just adding numbers to a list. It is providing the statistical weight needed to kill off some theories and give life to others. The data increasingly suggests that no single explanation fits all fast radio bursts. Instead, we are looking at a family of phenomena, a cosmic language of catastrophe where different dialects are spoken by magnetars, merging neutron stars and perhaps other engines we have yet to dream of. Every new ping in CHIME data is another word in that language, bringing us closer to understanding the universe's most violent whispers. Deep within the swirling heart of our own galaxy lies a different kind of enigma. While we scan distant stars for whispers, the core of the Milky Way itself broadcasts a symphony of strange and flickering signals we are only beginning to decode. This region, dominated by the supermassive black hole Sagittarius, a star, is a cosmic pressure cooker of unimaginable gravity, magnetic fields, and turbulent plasma. It is an environment so extreme that the normal rules of physics are stretched to their breaking point, and the radio waves it emits are unlike anything else in the sky. One of the most puzzling performers in this chaotic orchestra is a source known as GCRTJ 1745-3009. Discovered in 2002, this object does not behave like a star, a pulsar, or any known celestial body. For about an hour, it erupts in a brilliant burst of radio waves, becoming one of the brightest objects in the galactic center at that frequency. Then, just as suddenly, it fades back into the noise. These outbursts are not random. They repeat roughly every 77 minutes, but only for a few months at a time before the source goes quiet for years. It is a cosmic strobe light with an unreliable timer. The leading theory suggests it could be a type of magnetar, a highly magnetized neutron star, but one with a twist. Its location in the intense gravitational and magnetic environment of the galactic center might be triggering unusual outbursts, or perhaps it is interacting with the dense plasma swirling around the central black hole. The truth is, GCRTJ 1745-3009 fits no neat category. It is a reminder that even in our own backyard, the universe still holds cards we have not seen. But the mysteries do not end with flickering points of light. Stretching across the galactic center are vast magnetized filaments like ghostly threads woven through the darkness. These structures, some of them dozens of light years long but only a few light years wide, glow with synchrotron radiation, meaning they are made of electrons spiraling at near light speed through immense magnetic fields. They look like cosmic violin strings, silent and immense. Their origin is one of the great outstanding puzzles of galactic astronomy. Did they form from the powerful winds and outflows of the central black hole? Or are they the result of interactions between massive clouds of gas, their magnetic fields pulled and braided into these incredible shapes? They may even be cosmic relics, the remnants of an ancient eruption from Sagittarius, a star that occurred millions of years ago. These filaments are not just beautiful, they are signposts pointing to the immense and poorly understood forces at work in the heart of every galaxy. Every strange signal from the galactic center, every flicker and filament, is a direct probe into the most violent physics in our cosmic neighborhood. They challenge our models of how plasma behaves under such extreme duress and how black holes influence the space around them not just through gravity, but through powerful magnetic tantrums. To understand these signals is to begin to understand the furious, hidden engine that powers the Milky Way itself. The furious heart of our galaxy speaks in radio waves and X-rays, but perhaps the universe's quietest, most profound signal is one we cannot see at all. For decades, the hunt for dark matter has been a story of indirect evidence of its gravitational pull on galaxies and the bending of light across the cosmos. Then, in 2014, a team of astronomers analyzing data from the European Space Agency's XMM Newton telescope announced something startling. They had found a faint, persistent line in the X-ray spectrum, a tiny spike of energy at 3.5 kiloelectronvolts or 3.5 keV, emanating from the Perseus galaxy cluster and later from the Andromeda galaxy. This was not the broad, messy emission from hot gas. It was a sharp spectral line, the kind produced when an atom or a particle makes a specific quantum leap. The problem was no known atom or molecule in the universe emits X-rays at that precise energy. So what was it? The most tantalizing and controversial hypothesis was that we were finally seeing dark matter itself. Specifically, the signal could be the death rattle of a hypothetical particle called a sterile neutrino. If this particle exists, it would be incredibly faint and massive, only interacting through gravity and the weak nuclear force. Theory suggested that, very rarely, one of these sterile neutrinos could spontaneously decay into an ordinary neutrino and a photon, a particle of light. The energy of that photon would be a direct fingerprint of the sterile neutrino's mass. The 3.5 keV line fit the predicted profile perfectly. It was as if the invisible scaffolding of the universe had, for the briefest moment, flickered into view. The announcement ignited a fierce and ongoing debate within astrophysics. Other teams rushed to analyze data from different telescopes like NASA Chandra X-ray Observatory and Japan's Suzoku satellite. Some confirmed the line's presence in other galaxy clusters, strengthening the dark matter case. Others, however, found nothing but smooth X-ray backgrounds. The signal was at the very edge of detectability, a whisper so faint it blurred into the statistical noise of the instruments themselves. Critics argued it could be an artifact of the complex models used to subtract the background X-ray glow from hot plasma, or perhaps an unknown line from common elements like potassium or chlorine in a strange ionic state. The difficulty is profound. Confirming a signal of decaying dark matter requires not just seeing the line, but seeing it exactly where dark matter should be and nowhere else. It should be strongest in the dense, dark matter-rich cores of galaxy clusters and faint in empty voids. The data has been frustratingly ambiguous, supporting both the dark matter interpretation and more mundane astrophysical origins. If the 3.5 keV line were ever conclusively proven to be from dark matter, it would be a revolution on par with the discovery of the cosmic microwave background. It would crack open the 85% of the universe that has until now been a complete mystery. We would move from mapping dark matter's shadow by its gravity to studying its fundamental nature, its particle properties, and potentially its role in the formation of the very first structures in the cosmos. It would give us a new language to speak about the invisible architecture of everything. For now, the line remains a ghost in the X-ray data, a maybe, a possibility that hangs in the balance between a monumental discovery and a cosmic mirage. It is a reminder that sometimes the most important signals are not the loudest screams, but the faintest tremors in the fabric of reality itself. The faint X-ray line from dark matter is a whisper from the invisible, but sometimes the universe sends us a messenger we can actually see. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a tiny, fast-moving point of light that did not belong. It was not orbiting the sun, it was passing through, and its trajectory was unlike anything seen before. This was no asteroid from our own solar system. Calculations of its path revealed a stunning truth. It was the first confirmed interstellar object ever detected, a visitor from another star. They named it Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. At first, it was catalogued as a comet, but it showed no coma, the fuzzy cloud of gas and dust that forms when a comet's ice is warmed by the sun. It was then reclassified as an asteroid, a simple rocky body, but Oumuamua refused to fit any simple category. Its light curve, the pattern of its brightness as it tumbled, revealed an extraordinary shape. It was not round or lumpy like most asteroids. Instead, its brightness varied by a factor of 10 as it spun, suggesting an object that was at least 5 to 10 times longer than it was wide. Imagine a cigar or a pancake tumbling end over end through the void. This extreme proportions were unlike any natural object we had ever seen in our own solar system. Then came the second and more profound anomaly. As Oumuamua sped away from the sun, something was wrong with its trajectory. Even after accounting for the gravitational pull of the sun and planets, it was accelerating ever so slightly on its way out. Comets do this all the time. Their ices vaporize in the sun's heat, creating jets of gas that act like tiny thrusters. This is called non-gravitational acceleration. But Oumuamua had no visible coma, no detectable outgassing of water vapor or dust. It was accelerating in silence, so what was pushing it? The scientific community scrambled for natural explanations. Perhaps it was outgassing hydrogen, a gas that would be invisible to our telescopes. The object could be a hydrogen iceberg, a chunk of frozen primordial hydrogen from the cold depths of interstellar space, vaporizing in the sunlight. Or maybe it was made of solid nitrogen, like a piece chipped off a Pluto-like world in another system, with nitrogen sublimating and providing the thrust. These are ingenious ideas, but they require materials and formations that are, for now, purely theoretical. The lack of any visible debris or dust trail made these explanations feel like a tight squeeze. The puzzle of its silence and its acceleration led to a more speculative but scientifically framed hypothesis from Harvard astronomer Avi Loeb. Could Oumuamua be a piece of alien technology? Specifically, he suggested it might be a light sail, a thin, reflective sheet designed to be pushed by the radiation pressure of starlight. This would explain the non-gravitational acceleration without any visible outgassing. Its unusual shape could be the result of its design, a wide, thin sail that appeared elongated from certain angles as it tumbled. Loeb's proposal was not a declaration of discovery, but a call to consider all possibilities when the data resists conventional answers. He framed Oumuamua as a physical signal, a data packet delivered to our solar system. Whether it was a strange rock or a discarded artifact, its very existence and bizarre properties were a message, telling us that other star systems produce objects unlike anything we have at home. The debate it ignited was itself a kind of signal, a flare illuminating the boundaries of our knowledge and the limits of our imagination. Oumuamua is now far beyond the reach of our telescopes, a silent envoy speeding back into the darkness. We may never know its true nature, but its brief visit left an indelible mark, a reminder that sometimes the most enigmatic signals are not waves of light or sound, but solid pieces of a mystery passing right through our front yard. Oumuamua's silent passage reminds us that some mysteries are fleeting, but others beat with a steady, predictable rhythm. Among the chorus of cosmic crackles found by the CHIME telescope, one stands out as a true timekeeper. It is officially catalogued as FRB 180916, but astronomers have given it a more evocative nickname, the boomerang. This is not because it returns to us, but because its outbursts follow a pattern so reliable it feels like a cosmic clock. For roughly 4 days, the boomerang will fire off several fast radio bursts per hour. Then, for the next 12 days, it falls completely silent. This active and quiet cycle repeats with metronomic precision every 16.35 days. That periodicity is a golden clue. In the chaotic realm of extreme astrophysics, such a clean, repeating schedule points overwhelmingly to one thing: an orbit. The boomerang repeater is almost certainly not a lone object. It is part of a binary system, locked in a gravitational dance with a companion. The leading image is a neutron star, possibly a magnetar, orbiting another star or perhaps a black hole. For those 4 active days, the neutron star is passing through a specific point in its orbit, a region where conditions are just right to trigger the colossal burst. This could be where it plows through a dense wind streaming from its companion star, or where tidal forces and magnetic interactions reach a breaking point. The 12 days of silence correspond to the rest of its orbital journey, where those trigger conditions are not met. This simple, elegant explanation transforms the boomerang from a mere curiosity into a Rosetta Stone. Its period tells us the orbital separation of the system. The duration of the active window hints at the size of the triggering region. By studying the subtle changes in the bursts themselves during the active phase, astronomers can probe the environment around the neutron star in real time, sensing how the density of gas or the strength of magnetic fields changes along its path. The boomerang's steady rhythm is doing more than just identifying one system. It is providing a blueprint. It proves that at least a significant fraction of repeating fast radio bursts originate in binary environments. This immediately rules out models that require a single, isolated cataclysm. Instead, it points to a process that can be turned on and off by celestial mechanics, a repeating storm season in a distant star system. Every time the boomerang's activity window opens and closes on schedule, it whispers a fundamental truth about the universe, that even its most violent explosions can be choreographed by the silent, predictable dance of gravity. The universe's grand clockwork is matched by its subtler, more pervasive whispers. While we hunt for brilliant flashes and strange visitors, a faint, enigmatic glow blankets the entire sky. This signal is not a burst or a pulse, but a persistent hum in the microwave band of the spectrum, and it emanates from some of the darkest places we know. Look toward the constellation crux, the Southern Cross, and you will see a patch of perfect blackness blotting out the stars behind it. This is the coal sack, a dark nebula, a dense cloud of cold gas and dust so thick it blocks the light from the Milky Way. Common sense says such a cold, dark place should be silent, a void in the microwave sky. But our telescopes tell a different story. The coal sack and many dark nebulae like it actually glow with a mysterious microwave light. This is not the thermal radiation you would expect from warm dust. It is something else entirely, a phenomenon astronomers call anomalous microwave emission. For years, this pervasive signal was a major nuisance. It was an unexplained fog that confused measurements of the cosmic microwave background, the ancient afterglow of the Big Bang itself. Scientists had to carefully subtract this anomalous glow to see the primordial universe clearly, but they were left with a profound question: what was causing it? The radiation did not match the signatures of any known atomic or molecular process. It was too broad and too strong to come from simple heated dust grains. The leading theory, developed over the past 2 decades, is as fascinating as it is strange. The signal may be coming from the smallest pieces of dust in the universe, grains only a nanometer across, smaller than a virus. These are not just specks of rock or carbon, they are thought to be asymmetric molecules like tiny, lopsided tops. When ultraviolet light from nearby stars strikes them, they begin to spin, not just slowly but billions of times per second. This furious, frantic rotation causes them to emit radiation at microwave frequencies through a process called electric dipole emission. Think of it as the cosmic equivalent of a hummingbird's wings, a blur of motion creating a persistent, distinctive hum. These spinning nanograins would be a completely new component of the interstellar medium, a hidden population of the tiniest machinery, converting starlight into microwave whispers. Yet, for all the elegance of this theory, the anomalous microwave emission remains an active frontier. We have not yet directly imaged these spinning dust grains. Their exact chemical composition is unknown. Are they tiny diamonds, sheets of carbon, or complex organic molecules? Other explanations still linger, involving more exotic magnetic effects or interactions within the dust clouds themselves. This signal is a reminder that even the darkest, seemingly empty corners of space are alive with faint, complex physics. It is a background hum that fills the galaxy, a testament to processes occurring on a scale so small we can only infer them from the gentle glow they leave behind. Solving this mystery is not just about cataloging another emission. It is about mapping the complete life cycle of cosmic dust, from the ashes of dead stars to the building blocks of future planets. Every unexplained whisper, even this faint microwave sigh from the dark, is a chapter in the story of how our material universe came to be. While spinning dust grains hum in the dark, a nearby stellar corpse screams in a light our eyes cannot see. Just over 800 light-years away, in the constellation Gemini, lies the Geminga pulsar. This is the ghost of a massive star that exploded over 300,000 years ago, leaving behind a rapidly spinning neutron star. For decades, Geminga was known as a steady, if faint, radio source and a bright emitter of X-rays. But then, we learned to see it in a new light, the highest energy light in the universe. Using observatories like the High-Altitude Water Cherenkov or Hawk telescope in Mexico, astronomers did not just see Geminga, the point of light. They discovered it was surrounded by a colossal, faint halo stretching over 20 light-years across. This halo glows with tera-electronvolt gamma rays, photons carrying trillions of times more energy than visible light. It is a ghostly shroud of pure, unimaginable violence. The creation of this halo is a story of cosmic acceleration. The Geminga pulsar is not just a spinning magnet, it is a cosmic powerhouse blasting out a relentless wind of charged particles, electrons and positrons, moving at nearly the speed of light. As this hurricane of particles slams into the thin gas of the interstellar medium, it creates a colossal shock wave. Within that turbulent boundary, particles are whipped to even higher energies, and when they collide with photons from the cosmic microwave background, they transform into the ultra-high energy gamma rays we detect as the TV halo. This discovery was a revelation in multi-messenger astronomy, the practice of observing the same object across different types of signals, from radio waves to gamma rays. By combining the view from Hawk with X-ray and radio data, scientists could piece together the complete life cycle of Geminga's Fury. They could trace how the energy from its spinning core is converted into a particle wind, and how that wind then paints a giant, invisible beacon across interstellar space. The Geminga halo is more than just a pretty picture. It solves a practical cosmic mystery. For years, satellites have detected an unexplained fog of high-energy positrons, the antimatter twins of electrons raining down on Earth. The leading suspect for their origin has been nearby pulsars like Geminga, acting as natural particle accelerators. The size and brightness of the TV halo provide the smoking gun evidence. They prove that Geminga is indeed confining and accelerating these particles, and that a significant fraction are escaping into the galaxy, some eventually finding their way to our detectors. Here, the enigmatic signal is not a mysterious blip, but a vast, structured glow that tells a complete story. It reveals the invisible aftermath of a star's death, the hidden mechanics of a cosmic engine, and the answer to a decades-old question about the antimatter in our own backyard. It teaches us that some of the universe's most profound messages are not written in sudden bursts, but in the patient, expansive light of ancient explosions. The quiet aftermath of the Periton signal was as important as the initial excitement. When that strong, narrowband whisper from HD 164595 faded, it did not vanish into obscurity. It triggered a meticulously planned global response. This moment became a real-world test of the protocols that guide the search for extraterrestrial intelligence, a framework designed to replace speculation with systematic evidence. The first and most critical rule is verification. A single detection, no matter how promising, is not enough. It could be interference, an instrumental glitch, or a statistical fluke. The signal must be observed again, independently, by other telescopes. Within days of the news breaking, two of the world's most powerful SETI facilities swung into action. The Allen Telescope Array in California, a field of 42 dishes designed specifically for this purpose, began a deep listening campaign. Simultaneously, the Green Bank Telescope in West Virginia, the largest fully steerable radio telescope on Earth, pointed its colossal dish toward that distant sun-like star. They listened not just on the original frequency, but across a wide band, searching for any repeat of the signal or any other anomalous emission. For over 2 months, these instruments gathered data, straining to hear an echo of that first tantalizing ping. The second pillar of the protocol is transparency. Unlike secretive government projects, modern SETI operates in the open. The teams at the Allen Array and Green Bank publicly announced their follow-up plans and later published their null results, a crucial act of scientific honesty. They shared not just their conclusions, but their methods, allowing the entire community to scrutinize the process. This open collaboration prevents a single group from clinging to a cherished hypothesis and allows the collective weight of evidence to guide the field. The third step is elimination. Scientists methodically work through a checklist of possible explanations, starting with the most mundane. Could the signal be from a passing satellite? An aircraft, a ground-based transmitter, or perhaps an artifact within the telescope's own electronics? In the case of HD 164595, the most plausible answer emerged from this process. The signal's characteristics and its failure to reappear pointed overwhelmingly to a human-made source, likely a satellite that had not been fully accounted for in the complex models of Earth's radio frequency environment. The star itself was silent. This coordinated effort, though it ended without a discovery, was a resounding success for the protocols themselves. It proved the system works. It demonstrated that the global scientific community can mobilize rapidly to investigate a candidate, collaborate transparently, and reach a consensus based on evidence rather than hope. Every potential signal that passes through this rigorous gauntlet and survives emerges not as a maybe, but as a revolution. The silent star HD 164595 taught us that the path to a confirmed hello is paved with disciplined listening, shared skepticism, and the courage to report a null result. It is through this careful, unglamorous work that we prepare ourselves to recognize the real thing when it finally comes. Gliese 581 is a name that carries the weight of a dream. This red dwarf star, just over 20 light-years away, became a focal point for hope because of its family of planets. Among them, Gliese 581g, discovered in 2010, was announced as one of the first potentially Earth-like worlds found in its star's habitable zone, the region where liquid water could exist. The very idea of a habitable world so close made it a prime target for listening, and soon whispers of a discovery began to circulate. In 2008, before Planet G was even confirmed, an Australian news report claimed that astronomers using the University of Tasmania's radio telescope had detected a suspicious, unexplained radio burst from the direction of the Gliese 581 system. The story spread like wildfire across the internet, fueled by the tantalizing possibility of a signal from a life-friendly star. However, the scientists involved quickly and firmly refuted the claim. They clarified that the signal in question was almost certainly human-made interference, a common culprit that had been misinterpreted in the excitement of the moment. This first incident became a cautionary tale about how easily the desire for contact can outpace the rigor of the data. Yet the allure of Gliese 581 refused to fade. 4 years later, in 2012, a new claim emerged, this time from a team of Russian astronomers at the Zelenchekskaya Observatory. They announced they had detected a strong, non-repeating signal from the direction of Gliese 581 that seemed to originate from the star itself. The signal was a sharp spike in the spectrum, and the team, led by a researcher named Reappear, suggested it warranted serious investigation as a potential technosignature. Once again, the news sparked a media frenzy and public imagination. And once again, the broader scientific community responded with deep skepticism. Other SETI researchers pointed out that the signal was detected at a single frequency with a very narrow bandwidth, a pattern that is highly susceptible to being produced by terrestrial sources or instrumental noise. More critically, the signal was never independently verified by any other observatory. The SETI Institute's own Allen telescope array listened intently to Gliese 581 and heard nothing unusual. Without that crucial repeatability and independent confirmation, the Russian claim, like the Australian one before it, dissolved into the background noise of unverified anomalies. These twin controversies around Gliese 581 highlight a profound and emotional challenge at the heart of the search for intelligence. When we discover a planet that looks even remotely like home, our longing to not be alone becomes a powerful filter. We project our hopes onto the data, sometimes seeing patterns where none exist. Every unexplained blip from the direction of a habitable world feels momentous, a potential hello waiting to be decoded. This psychological pull makes the discipline of the scientific method more vital than ever. The process demands that extraordinary claims be met with extraordinary evidence, not just a single, unrepeatable anomaly. It requires the painful but necessary step of inviting other scientists to try and prove you wrong. The Gliese 581 signals, both ultimately dismissed, serve as essential reminders that the universe is filled with natural and human-made radiostatic, and our greatest tool for sifting through it is not just better technology, but relentless skepticism. The dream of a signal from a world like Gliese 581g remains alive, but the path to confirming it is paved with quiet, patient listening and the courage to dismiss the false alarms that make our hearts race. The dream of a habitable world can make us hear what we wish for, but sometimes the universe's greatest tricksters are not in distant galaxies but in our own kitchens. For years, as the search for fast radio bursts intensified, astronomers at the Parkes radio telescope in Australia kept detecting a frustrating class of signals. They were named Puritans after the mythical winged stags that cast the shadows of men. The name was perfect, for these signals were cosmic shadows cast by something utterly mundane. They shared key characteristics with genuine fast radio bursts, exhibiting that telltale dispersion that made them look like they had traveled across the vast interstellar medium. They were the ultimate mimics, ghostly imitations that slipped past initial filters and appeared to come from the sky itself. This created a maddening problem. Were some of these Puritans actually real cosmic bursts, or was the entire field being polluted by an unknown local source? The mystery consumed researchers for years, threatening to undermine confidence in every new detection. The hunt for the source became a detective story played out across the observatory grounds. Scientists meticulously logged every Puritan, noting its time, frequency, and direction. They began to see a pattern. The signals only occurred during weekday daylight hours and never at night or on weekends. This was the first major clue pointing squarely to human activity. The final breakthrough came from an ingenious bit of forensic work. The team installed a radio monitor at the telescope site to watch for interference in real time. Then they waited. The culprit was revealed in a moment of delicious absurdity. The Puritans were being generated by the observatory's staff kitchen. Specifically, they were caused by the opening of a microwave oven door before the timer had finished. A running microwave emits a localized burst of radio waves, which is contained by the metal shielding of the oven. But if you interrupt the cycle and swing the door open early, that burst escapes. If the telescope happens to be pointing in just the right direction at that exact millisecond, the radio pulse reflects off the metal buildings or the surrounding landscape and enters the receiver, picking up a dispersed, cosmic-looking signature along the way. The humble act of reheating lunch was perfectly impersonating a cataclysm from billions of light years away. The resolution of the Puritan mystery was not an embarrassing failure, but a vital victory for the scientific process. It forced the development of stricter data vetting protocols. Now, observatories use multiple, geographically separated telescopes to confirm a signal. A true fast radio burst will appear in the data from two distant sites with a tiny time delay, proving it came from space. A Puritan or any other local interference will hit one telescope and not the other. This episode taught astronomers a profound lesson in humility, that before you can listen to the universe, you must first learn to silence the noise of your own world. It is a reminder that the most enigmatic signals are sometimes the ones that lead us not outward to the stars, but back to our own reflection. Hidden in the faintest radio whispers from the dawn of time, a different kind of anomaly emerged. In 2018, a small, ground-based antenna in the remote Australian outback, part of the experiment to detect the global epoch of reionization signature, or edges, made a claim that sent shockwaves through cosmology. It reported hearing the echo of the universe's first starlight, a signal so old it traveled for over 13 billion years to reach us. This was not a burst or a beacon, but a subtle dip in the cosmic radio background, a fingerprint left by the very first stars as they flickered on in the primordial dark. The theory was elegant. Before stars existed, the early universe was filled with a fog of neutral hydrogen gas. This gas naturally emits and absorbs radio waves at a specific frequency, one that gets stretched over cosmic time as the universe expands. When the first massive, brilliant stars ignited, their intense ultraviolet radiation began to heat this cosmic fog. The Edge's antenna was tuned to listen for the telltale sign of that heating process, a slight absorption dip in the radio spectrum as the cooler hydrogen gas soaked up background radiation. They found the dip right where it should be, but its depth was terrifying. The signal was twice as strong, or the absorption twice as deep, as any standard cosmological model could possibly explain. It was as if the primordial hydrogen was far colder than anyone predicted, or the background radiation bathing it was far hotter. Either scenario breaks our understanding of the universe's infancy. To explain such profound cold so early, physicists turned to a radical idea: dark matter. Perhaps in that ancient era, the invisible dark matter that fills space was interacting with the normal hydrogen gas in a way we never anticipated. If dark matter particles were cool and able to collide with hydrogen atoms, they could have acted like a cosmic coolant, siphoning away thermal energy and chilling the gas to temperatures the standard model cannot achieve. This single, faint dip in a radiograph, if confirmed, would be our first direct evidence of dark matter interacting with normal matter through any force other than gravity. It would rewrite the opening chapters of cosmic history, yet extraordinary claims demand extraordinary proof. The EDGE's result is phenomenally difficult to verify. The signal is incredibly faint, buried in a sea of foreground radio noise from our own galaxy, which is thousands of times brighter. Separating the cosmic dawn signal from this local static is a monumental task, akin to listening for a single whispered syllable in a roaring stadium. Since the announcement, other teams have tried to confirm the detection using different instruments and methods, with mixed and inconclusive results. Some see hints of the signal, others see nothing but noise. The scientific community remains cautiously skeptical, pushing for more data from new experiments designed with even greater precision. This is the razor's edge of discovery, where a whisper from the dawn of everything hints at a fundamental revolution, but has not yet spoken loudly enough for all to hear. The universe's faintest whispers from its dawn are matched by ghostly giants hiding in plain sight. In 2019, astronomers working with the Australian Square Kilometre Array Pathfinder, or ASCAP, were mapping the night sky in radio waves when they stumbled upon something that should not exist. They found faint, perfect circles of radio emission floating in the darkness between galaxies. These were not smudges or blobs, but crisp, circular rings, like cosmic smoke rings blown into the void. They named them odd radio circles, or ORC. The mystery began with what they were not. When scientists pointed optical, infrared, and X-ray telescopes at the exact same coordinates, they saw nothing at all. The circles were completely invisible at every other wavelength. They existed only as ghosts in the radio spectrum, immense and silent. Their scale is almost incomprehensible. Each ORC is hundreds of thousands of light years across, meaning it could easily engulf an entire galaxy like our Milky Way. Yet for all their size, they are incredibly faint and diffuse, which is why it took a sensitive, wide-field radio telescope like ASCAP to finally see them. So what could possibly create such a perfect, enormous, and invisible ring? The leading theory is a titanic shockwave from a cataclysm of galactic proportions. One possibility is a starburst wind on a scale we can barely imagine. If two large galaxies collided, the furious burst of star formation that follows could drive a spherical tsunami of gas and magnetic fields outwards at nearly the speed of light. When this colossal bubble slams into the thin intergalactic medium, it could create a standing shockwave that lights up as a radio ring, a cosmic echo of the merger's most violent moment. Another compelling idea links them to the aftermath of a central galactic black hole's meal. If a supermassive black hole at a galaxy's core has a sudden, enormous feast, swallowing a vast cloud of gas or even another black hole, the energy released could blast a jet of material out along its poles. From our distant perspective, looking down the barrel of such a jet, the expanding shock front might appear as a perfect circle. There is even a more exotic suggestion that ORCs could be the throats of wormholes, or the imprint of a collision between parallel universes in string theory, though these remain highly speculative. The true power of the ORC discovery is not in any single explanation, but in the simple, stunning fact of their existence. They represent an entirely new class of celestial object, something never predicted and completely unknown just a few years ago. It is a humbling reminder that our maps of the cosmos are still incomplete, that giant, ghostly rings can hide between the stars, waiting for us to look at the sky in just the right way. Every new ORC detected is a question mark written across hundreds of thousands of light years, a silent signal that the universe still has profound surprises in store. The ghostly rings of ORCs remind us the cosmos is filled with structures we never predicted. But what about the structures a civilization might build? To search for intelligence, we must first define what we are listening for, and one powerful framework for that is the Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964. It categorizes civilizations not by their politics or art, but by a single, measurable metric, their total energy consumption. A Type I civilization has mastered all the energy available on its home planet, harnessing the power of volcanoes, weather, and sunlight that falls on its world. We, humanity, are not even a full Type I yet, but we are approaching it, our global energy use flickering like a candle in the dark. A Type Roman II civilization is a stellar species. It has learned to capture and utilize the entire energy output of its star. This is the realm of theoretical megastructures, like a Dyson sphere or swarm, a vast array of collectors that would completely enclose the sun, transforming its light into usable power for computation, construction, or communication on an unimaginable scale. A Type Roman III civilization transcends its star. It is a galactic empire controlling the energy output of every star in its home galaxy, billions of suns harnessed in a network spanning light years. This scale gives us a blueprint for the signals we might hear. A Type I civilization might be detectable only by the narrowband radio or laser leaks of its communication systems, accidental broadcasts like our own television and radar signals that seep into space. Finding such a whisper across interstellar distances is like trying to hear a single conversation in a hurricane. A Type Roman II civilization, however, would be far harder to hide. The waste heat from its stellar engineering would be a glaring infrared signature, a star that shines brightly in the infrared but is oddly dim in visible light. It might also produce powerful, directed beams for propulsion or communication, intentional signals meant to be found. A Type Roman III civilization might reshape the very structure of its galaxy, its activities perhaps visible as entire clusters of stars that flicker or go dark in unnatural patterns, or as a pervasive infrared glow from a galaxy that looks too quiet for its stellar population. Our search, then, is a hunt across this spectrum of possibilities, but it is a hunt within an unimaginably vast cosmic haystack. The haystack is defined by multiple dimensions, not just space, but frequency, time, and signal type. We must search across billions of stars, across a radio spectrum that is virtually infinite in its breadth, and we must listen at the right moment in a civilization's technological lifespan, which might be fleeting. We are looking for a needle we cannot fully describe in a haystack whose size defies comprehension. Yet the Kardashev scale gives that needle a shape. It tells us to look not just for a halo, but for the silhouette of an immense and purposeful shadow against the stars, the signature of a universe not just inhabited but engineered. But to find that shadow, we need eyes that can see in the dark on a scale we have never before attempted. That future is being built right now across two continents. In the remote deserts of South Africa and Western Australia, a technological titan is slowly taking shape, the Square Kilometre Array. The name is a literal promise. Its combined dishes and antennas will eventually gather radio waves over a total area of 1 square kilometre. This is not just a bigger telescope, it is a new kind of ear for the cosmos. Its sensitivity will be staggering, able to detect an airport radar on a planet orbiting a star tens of light years away. Its survey speed will be equally transformative, scanning the sky thousands of times faster than any current system. this combination will change everything. In the hunt for fast radio bursts, the SKA will move from catching rare specimens to conducting a census. It will detect not dozens, not hundreds, but potentially thousands of these bursts every single day. Each one will be pinpointed with exquisite precision, allowing us to instantly identify its host galaxy and understand the environments that breed these cosmic explosions. We will see patterns emerge from the chaos, finally distinguishing the different dialects in this language of catastrophe. Beyond the bursts, the SKA will perform a cosmic ultrasound. It will map the faint radio glow of neutral hydrogen, the universe's most basic building block, across billions of light years and deep into the past. This will let us watch the large-scale structure of the cosmos evolve, tracing the invisible filaments of dark matter that guide the formation of galaxies. We will see the universe's skeleton in radio light, and for the search for intelligence, the SKA represents our most profound effort yet. It will conduct the ultimate SETI survey, monitoring millions of stars simultaneously across a vast range of frequencies. It will be sensitive enough to hear the equivalent of Earth's own television and radar leakage from the nearest stellar systems. More importantly, it will be able to distinguish between natural cosmic static and the narrow, engineered signals of technology with unprecedented clarity. The peritons and false alarms that have haunted previous searches will be filtered out by the sheer volume of confirming data from its vast intercontinental network. The square-kilometer array will not just seek answers to our current mysteries, it is guaranteed to discover entirely new ones. It will hear whispers from the cosmic dawn with such fidelity that the controversy over the edge's signal will be settled. It may find more odd radio circles, revealing if they are common or rare, and perhaps catching one in the act of formation. It could detect the thermal glow of a Dyson swarm around a nearby star, or the organized radio chatter of a civilization just learning to broadcast. This is the promise of the next generation, a machine built not just to observe the universe, but to listen to its deepest conversations. With the SKA, we are not just turning up the volume, we are learning to understand the grammar of the cosmos itself. 25 signals, each a cosmic question mark, and yet the most profound signal of all may be the one we have not received. After decades of listening, our most sensitive instruments have heard no clear, unambiguous message, no repeating pattern that shouts intelligence. This absence has a name, the Great Silence, and it presents a paradox as deep as any flash from the void. If the universe is so vast and old, with billions of potentially habitable worlds, then where is everybody? The silence is not empty, it is filled with possible answers, each more humbling than the last. Perhaps the development of complex, communicative life is extraordinarily rare, a cosmic accident that has happened only once. The chain from a stable star to a suitable planet, to the genesis of life, to multicellular organisms, to intelligent toolmakers, to a technological civilization might be so fragile that it breaks at almost every link. We could be the first, or we could be alone. Another possibility is that the window for detection is tragically narrow. A civilization might bloom with radio technology for only a few centuries before it either destroys itself or evolves beyond broadcasting into a state we cannot perceive. We have been loudly leaking radio and television signals for less than 100 years, a blink in cosmic time. If other civilizations had their brief radio age 1,000,000 years ago, or will have it 1,000,000 years from now, we would miss each other completely, ships passing in an eternal night. The most transformative idea is that we are listening for the wrong thing. A civilization just a few hundred years more advanced than us might use technologies as far beyond our radio telescopes as those telescopes are beyond smoke signals. Communication could happen through modulated neutrinos, quantum entanglement, or structures in spacetime itself, channels utterly invisible to our current science. Or perhaps advanced societies consciously choose silence, observing a cosmic quarantine to protect younger species like ours, or to avoid attracting the attention of something unknown. They might live within matryoshka brains, supercomputers encasing their stars, their entire existence a contemplative inner world that emits nothing but waste heat. The great silence, then, is not proof of our solitude, but a mirror reflecting the limits of our infancy. We are like a child on a beach shouting into a shell, wondering why the ocean does not shout back in our own language. Our search has just begun. Every enigmatic signal, every mysterious flash is a lesson in how to listen better. They teach us that the universe is far stranger, more creative, and more violent than we ever dreamed. Whether the next great discovery is a natural cataclysm or a whispered hello, it will redefine us. So we keep listening, not just with our telescopes, but with our imagination, ready for the universe to speak in a voice we have only just begun to understand. From the lonely cry of the wow signal to the ghostly rings between galaxies, this journey reveals a cosmos alive with questions. Each of these 25 enigmatic signals, whether a fleeting burst of impossible energy or a persistent, unexplained glow, represents a frontier. They are not merely anomalies to be filed away. They are the universe's way of teaching us how little we know. Every time a mystery like the Puritans is solved, tracing a cosmic scream back to a microwave oven, we refine our tools and sharpen our questions. And every time a puzzle like dark matter's faint X-ray whisper or the perfect circles of ORCs remains stubbornly open, it forces us to invent new physics, to imagine possibilities beyond the pages of any textbook. This is the true engine of discovery, a relentless curiosity fueled by the static between the stars. So the next time you find yourself beneath a clear night sky, remember this: you are not looking at a silent, static tapestry. You are gazing into a cosmic ocean of radio whispers and gamma-ray shouts, of spinning dust and stellar corpses, of echoes from the dawn of time and shadows of engineering we cannot yet conceive. The silence is an illusion. The universe is speaking in 1,000 voices, and we have only just learned to cup our ears. Stay curious, for the next great signal, the next revelation that rewrites our story, is already racing toward us through the dark.